Thanks. Morning, everyone. Welcome to the presentation on how not to write the PCI controller drivers in Linux kernel. I'm Manivannan Sadasivam. I work as a senior kernel engineer at the Qualcomm learning team of Linaro. So why am I doing this talk? So I'm reviewing and maintaining the PCI controller drivers for some time, and I have identified some recurring pattern of mistakes that developers do. And I often point those mistakes during review cycle, but I thought about just documenting everything in this presentation so that it can serve as a reference in the future. And one nice side effect of that is that if I see those mistakes again in the review process, I can just point to this talk instead of just going and asking them to fix or how to. So, okay, let's get started. I'll just give a quick introduction to PCI, and then what are the PCI controller drivers, and then I'll point out the common mistakes that developers often do, and then offer some solutions for them. So PCI in a nutshell, so PCI stands for Peripheral Component Interconnect. That was the old standard developed by Intel back in 1994. And it got superseded by PCI Express. And even though it's software compatible with PCI, nobody uses PCI these days. Everything is PCI. So, I mean, I use PCI and PCI interchangeably, but I'm only referring to PCIe. So PCI actually, people use PCI for a lot of things, and it was mainly used for port expansion, for connecting the devices to your host PCs or servers, laptops, and even for mobile in the future, I guess PCI will come into picture. And the PCI SIG, the committee actually markets this as a plug-and-play bus. In theory, it is plug-and-play, but in practical, it never works like that. And if you have worked on PCI with Qualcomm devices, you will know what I'm saying. So the PCIe specification itself was developed by a group of engineers in Intel, and then later the specification got handed over to PCI SIG. And ever since, the SIG actually works on maintaining the spec with the help of engineers from other companies also. So PCI works in lanes. So we have TX-RX differential path transducers lanes, and it can go from one lane to 3264. So PCI supports a couple of power management models, the software managed power management, which is PCI PM, and then the hardware managed power management, which is ASPM, active state power management. And it also supports I/O virtualization with the help of SR-IOV these days. So let's take a look at the architecture of PCI. So PCI is actually a point-to-point topology, which means you can actually connect one endpoint to the root complex at a time. And if you want to connect more endpoints, then you need to have some sort of switches in between. So what we have in this picture is that we have the host SoC, and it has the root complex in it, and inside the root complex we have the host bridge and a couple of PCI bridges. So the host bridge is the one that translates the instructions from the CPU to the PCI TLPs and whatnot. And it is actually connected to a couple of PCI bridges here. So the PCI bridges are usually for port expansion or bus expansion. And in this example, I have used a couple of PCI bridges. So if that's the case, your SoC will support 2 PCI buses, and then you can connect 2 PCI endpoints to that. Or if you want to connect more endpoints, you connect a switch, and then you just multiply the devices. So each device in the PCI bus is actually identified using the bus device identifier. We call it BDF. And we have 8-bit allocated for the buses, 5-bit for devices, and 3-bit for functions. So that accumulates to 256, 82, and 8. That's the theoretical limit of number of devices, buses, and functions you can connect in a bus, actually. So as I said, if you want to connect more devices to this point-to-point topology, you would connect the PCI switches there, and PCI switches are nothing but the interconnection of PCI bridges in between. So it have one upstream bridge and multiple downstream bridges in between. So let's take a look at PCI and how it is actually supported in Linux kernel. So Linux kernel actually supported PCI from the legacy PCI from the early 1.3 release, and PCIe since version 2.6. The code organization, so we have the core drivers, which are common to PCI and PCIe, living under drivers PCI. So you can see bunch of files over there. And we have the PCI specific drivers under the PCI subdirectory. So these are like PCIe core specific features like ASPM, AR, TPC, etc. They live under this subdirectory. And then we have this PCI controller drivers. That's what I'm going to focus on this presentation. And these controller drivers are primarily used for controlling your host bridge that I mentioned in the last slide. And we have this PCI endpoint core, which is relatively new. I'm also maintaining this one. And this one is pretty interesting because Linux has been used on the host machines only. I mean, PCI on the host. So Linux usually controls the host machine, and then you can connect endpoint devices to it. But this endpoint core allows Linux to run on those tiny endpoint devices like your NVMe SSDs or WLAN devices. You can actually, I mean, with the help of the endpoint core, you can actually put Linux onto it, and you can actually make Linux work as an endpoint device. We recently merged NVMe endpoint function driver support with the help of Western Digital, and with that you can actually make Linux emulate the NVMe SSD to the host over PCI, which is pretty interesting. So, and finally we have the PCI client drivers, and that is actually scattered all over the place because the PCI client drivers are nothing but the device drivers of your PCI device, like GPUs, Ethernet, WLAN, NVMe, right? And these are all actually under their respective subsystems in kernel. And I am going to focus on PCI controller drivers in this presentation, as I said. So let's take a look at them and what they do. So the first thing is that they need to control the host bridge, right? So for that, they need to initialize the resources of the host bridge, like clock, regulators, power domains, etc., specific to the host bridge. And once those resources are initialized, the controller drivers usually call this PCI allow host bridge API, which just initializes few internal structures of host bridge. And then the controller drivers usually set up root ports. As I mentioned in the last picture, there can be multiple PCI bridges in your SoC, and some SoCs have only single root ports. The root ports are nothing but the PCI bridges or slots. So if you have multiple root ports, then you need to set up them, and then some root complex also work as a MSI or MSIX controllers as well. So if you have inbuilt controllers, then you need to set up those kind of controllers. And if you do not have any inbuilt controllers, then usually some sort of interrupt controller will be providing that support. So you need to just do some mapping to make sure that interrupts are routed accordingly. And this is the important step of PCI controller driver. It needs to set up the address translation unit for accessing the device. So each device will be having some sort of memory or I/O region, and in order to access those region, the controller driver has to set up some address translation, and we usually call this outbound address translation, because the translation goes from the host to the endpoint, which is in the outbound direction. So you need to set up that, and then if your RC has the DMA capability, you also need to set up some DMA, if there is an inbuilt DMA controller, you need to set up it. And then finally, you need to start the LTSSM. LTSSM is nothing but the link training state machine. That's the final state where you can say that, okay, you can the host controller driver can issue order to the PCI bus to start link training, so that everything has been set up perfectly. And once the link training actually passes, you will go and enumerate the endpoint devices by calling the PCI host probe. And even if the LTSSM state machine fails, which means that no endpoints are actually connected, then we would encourage the controller drivers to just not fail the probe and then just continue to leave the LTSSM in the detect idle state, because the endpoint may get inserted in the future, right? During runtime and all. That's why I said even though the PCI spec itself is marketed as plug and play, wouldn't work in practice, because some drivers actually fail probe if they don't see the devices during this driver probe. So that's unfortunate. Okay, let's take a look at the common mistakes and some solutions for fixing them. So first mistake that people often do is not describing the root ports in the firmware. The firmware, I'm mostly referring to device tree because it doesn't apply to ACPI. And on the device tree, we have this PCI device tree node for, the device node for the PCI root complex or the host bridge. And those root complex node often have the port specific properties or the bridge specific properties. So as you can see here, the PHYs and the reset wake GPIOs all correspond to the PCI ports or bridges. And since they're most likely only one root port per SoC, so what developers usually do is they will stuff everything to this root port or host bridge device tree nodes, and their controller driver will just parse them and then they'll just work. Even though it just works, the problem is that once the hardware designer switches their mind to have multiple root ports or bridges per root complex, then obviously you need to have multiple root ports defined in the device tree. And in that case, your driver has to support the old legacy binding, which is everything in the root complex node, and then new binding, where everything is in the respective bridge nodes or root port nodes. And for fixing that, obvious solution is to move the root port's properties to root port like this. So this is the device tree node of the root port, and so we have actually moved the PHY and then the GPIO properties to here. And even for Qualcomm, we actually did it fairly recently. And as I told you before, it also suffers from the same problem that now we have to support the old legacy binding and also this new binding. So nowadays, if people are writing the new controller drivers, we actually encouraged developers to switch to this model. And then the second mistake is that people often define all the power supplies for the slots, PCI slots, and also the PCI endpoints also in the root complex node, like this. So we can see here these three power supply properties, they correspond to the PCI slots. And since there is only one slot per root complex, they just do this, and then they control everything in the PCI controller driver itself. It sort of works. But the problem is that, as I said, if there is some requirement to have more power supplies, and if the hardware designer decides to go out of the spec and then add some out-of-the-bone GPIO or something like that, then it'll go crazy. So the solution is to move those supplies to the respective device tree nodes, and in this case, you should move the slot power supplies to the respective PCI slot node. So here, the PCI slot device tree node has this supply properties right now. And okay, if you have defined those or moved those properties, you might wonder who is going to take care of them, because previously the controller driver was taking care of them. And the solution for that is power control driver. Thanks to Bartosz, who works for Linaro, he introduced this power control framework, which takes care of powering on the PCI devices, without the intervention from the PCI controller drivers. So you just need to enable this power control slot driver that I wrote in the last cycle. And this driver will take care of the supplies defined in the device tree node of the PCIe ports. And it actually works for the standard supplies. So these are the supplies that 12 volt, 3.3 volt, and 3.3 Vox are the standard supplies defined in the PCI electromechanical spec. And even if your device requires any sort of custom power supplies and all, you can just define them. And what I've done in the driver is just use the off regulator bulk API. So it'll just parse all the regulators at once. And I didn't hard code any of the supply names in the driver, so it'll just work. And there is one more solution to this problem. What if the endpoint node requires some custom supply, and if that custom supply is actually shared with the other subsystem in the kernel. So that's the case for Qualcomm Wi-Fi drivers, because the Wi-Fi drivers often, the Qualcomm Wi-Fi WLAN devices is a combination of Bluetooth and WLAN. So the Bluetooth subsystem and also the Wi-Fi subsystem needs to access the device, and for that you need to create some shared power sequencing framework, and that's for that use case we have this power sequencing framework that was also introduced by Bartosz. And so the power sequencing driver actually takes care of handling all these supplies, and these supplies actually link to the PMU node of the device. And so those supplies can be controlled from the Wi-Fi node and also from the Bluetooth node. So the Wi-Fi works on top of PCIe and Bluetooth works on top of UART. So these two nodes will point these supplies, and then this power control driver for PCIe will take care of enabling them. And this actually is required for complex supplies. If you have some standard supplies like just 12 volt, 3.3 volt supplies, then you can actually use the slot driver that I mentioned in the previous slide. And then the third mistake is that mapping of each outbound translation, because as I said, the important functionality of a controller driver is to set up the outbound translation window, because whenever you want to access the device using bar access or the config space access, you need to set up the outbound translation. And for that, you need to use this ATU. It stands for Address Translation Unit. And what most of the drivers right now, we have identified this mistake fairly recently. They do is that they actually do this outbound translation mapping for each config and bar access, which is pretty much inefficient, and it also adds latency. You can see here, this is the designware driver that is in the mainline right now. So it actually has this map bus callback, and this map bus callback will be called by the PCI core whenever your client driver wants to access the device. It can be a config space access or it can be a bar access. It just goes through, sorry, it mostly applies to config space access. It just goes through this callback, and in that callback we actually program this outbound ATU for each access, and which is very inefficient, and it adds latency because you have to set up this mapping every time. So what we offer to this mistake is that you just need to configure your controller in the ECAM mode. ECAM mode was introduced in, I think, PCIe 3.0. It's been there for quite a long time, but then people never really use it. I don't know, for some reason. And ECAM is the enhanced configuration access mechanism. It is defined by the PCI spec, and for enabling ECAM, you need to provide a region, memory region in your SoC or memory, and then configure it to in such a way that if you access that region, it actually turns out to translates to a PCI bus access for the corresponding device. So if you use this region, you can actually do the ECAM configuration in a couple of ways. First one will be doing it in the bootloader itself. So your bootloader will set up the ECAM translation before booting the operating system, and it will hand it over. This is how the ACPI sort of works. The translation actually happens in the BIOS, and then the OS will just parse the ECAM region and it will just use it. One advantage of this approach is that you do not need any dedicated controller driver in the next kernel. You can actually use this PCI host generic driver written by ARM. And this driver will detect the presence of ECAM mode, ECAM region, and then it will just use it for accessing the devices. And of course, the ECAM region has to be of enough range to cover all the buses or devices that you intend to access. And the theoretical limit is 256 megabytes. So, and the problem or downside to this approach is that it requires a firmware change. And if you have already deployed the devices out there, and you should actually modify the firmware in order to support this. And one more problem is that you cannot go and reset the host bridge. And what if there is a fatal AE or error, or some link down event happens, and you want to reset the host bridge? That unfortunately you cannot do with this approach, because this driver doesn't support that. And for that you need a dedicated driver, and that's the solution too. So you actually configure the ECAM mode in your controller driver itself. Even if you have an existing driver, you just go and enable the ECAM mode. That's what we actually did with the DesignWare driver right now for Qualcomm SoCs. The patch is under review. And there is a feature called config shift feature in the DesignWare spec. And we use that spec to enable ECAM mode in the controller drivers for Qualcomm SoCs. And advantage of this is that we can actually, all the control lies in the Linux kernel itself. So even if we want to reset the host bridge, we can do that. We actually do reset the host bridge in the Linux kernel because when link down even happens on Qualcomm platforms, we need to actually reset the whole root complex device. So for that thing, it just works with us. But the problem is that it requires a separate controller driver. So it's actually a trade-off. If you do not want to reset your host bridge or you just want it to work, just configure everything in the bootloader. Or if you want to have control in the kernel, just have a separate controller driver and configure ECAM mode. Okay, so this is the final mistake that people do, which is not specific to PCI because there is a shutdown callback for the platform drivers, and people usually confuse that shutdown callback with the remove callback, and they ignore the shutdown callback and just usually populate the remove callback, assuming that the remove callback will be called during the device shutdown or reboot. But unfortunately, it is not, and these two serve different purposes. Shutdown callback is to just quest the state of the device. Let's say if you have a device underneath this platform device, or it exposes a bus where multiple devices are connected, this shutdown callback ensures that all those devices are properly shut down, and then they will not issue any kind of transactions after this. And that's the purpose of the shutdown callback. It should not actually release any sort of resources of the driver, and that is the purpose of the remove callback. It should do shutdown, and also it should release all the resources obtained during the probe. And these two are separate. And people often get confused, and then they don't define the shutdown callback. And the problem with PCI controller drivers is that if you do not define the shutdown callback, the endpoint state machine might get messed up during a warm reboot. Let's say if you are rebooting your machine without turning off the power to the endpoint, then the endpoint will not detect the host reboot. So it will get confused when you do the warm reboot. So we have multiple bug reports pointing to this kind of same issue. So we encourage developers to add shutdown callback, and the shutdown callback has to do some series of steps. The first thing is that first and foremost step is to put the device into D3 cold. So D3 cold is the power of state, and for doing that, you need to send the PME turn off message, and then the endpoint has to acknowledge it. So you will wait for the PME to act message from the endpoint, and once that is received, you will go and assert the burst sideband GPIO, and once the burst is asserted, the endpoint will know that the power and reference clock will going to be cut off. So it will prepare for that, and then finally you will remove the power. Or you can actually do that from the controller driver, or you can let the power control driver to take care of it. So once your shutdown callback gets called, your power control driver will come in the picture, and then it will turn off the power to the devices. It's still work in progress. And that's pretty much it. And we still have 5 minutes of time. Any questions? Mike, do you have?
Great talk, thanks. The question is, do you know how many drivers in the main line still repeat these mistakes?
I mean, most of them do actually, unfortunately. I mean, as I said, some mistakes we actually identified fairly recently, like this ECAM mode thing we actually identified quite recently. So most of the controller drivers, almost 90% of them just have this mistake. So we need to fix them, yeah. But this is mostly for the, the folks who are writing the new controller drivers. So, yeah.
So is there any advantage in not using ECAM? And if there's no advantage, then why wouldn't the Linux community force people to adopt ECAM?
Oh no, I mean, there are certainly advantages. I think I have clarified that in the slide. Sorry if I'm not clear. I mean, if you do not use ECAM, as I said, you need to map each outbound access. And that is quite inefficient, right? Whenever you want to access the config space, you need to do the mapping.
Exactly, and since there's so many drawbacks, why isn't ECAM mandated?
Oh, ECAM mandated? Yeah. I mean, I don't know. I mean, it's the problem is that I think ECAM is not mandated by the spec. It is still optional, and people take use of it. I mean, I don't know why. I'm still unsure of it, so I don't know. But it's quite inefficient to not to use ECAM. Yeah.
Cool, thanks.
Yeah, I'm surprised you can set up ECAM at runtime because I thought it was a IP configuration actually.
Oh no, I mean,
Yeah. Do you know which design-aware PCI Express controller support ECAM mode? It is something old version support.
yes,
So
it is actually defined in the spec itself.
yeah, but I mean the design-aware spec is not publicly available. So I mean nobody know about this. So.
I mean, if you are a vendor, and obviously you will have access to the designer spec, and that is a config shift feature. And I think since the core feature is upstreamed, I mean, the patches are still under review. I don't think you, if you want to enable ECAM mode, and if your driver is your IP is designware based, you do not need to do anything. You just need to do some specific steps in your controller driver, like allocating enough region for the ECAM mode and all.
So you can allocate any physical memory in DDR memory? Or?
Yes, DDR memory, yes.
Oh yeah, nice.
Yeah.
I mean, it's nice. Huh? Okay.
I mean,
Good to know.
I mean, it has to be accessible by the PCI domain. That's
Yeah.
platform specific. But yeah, if you have like enough memory region of 256 MB, then you can actually use it. I mean, even if you can actually reduce that memory, you can actually limit the number of buses that your host bridge supports. So if you reduce that, you can still use 32 megabits of region for ECAM mode.
Okay. So yeah, I think why they use ATU is for memory usage because ATU only uses register memory, and when you go in the bootloader stuff, you don't want to allocate like 100 megabytes of memory to do ECAM, but it was like 15 years ago, so I mean, not anymore this use case. So yeah, you can use ECAM mode now.
It could be one of the reasons, but then as we found out in the Qualcomm SoCs, it has plenty of memory, like gigabytes of memory allocated for the PCI domain. It was all were left unused, and we just want a piece of it, 256. And
yeah, because I added ECAM mode in Zephyr.
Okay.
And I was lazy to add support for ATU for Synopsys controller. So now, no reason to not implement Synopsys controller in Zephyr. So, thanks for the presentation.
Thank you. Thanks, everyone. Thank you.